So today we will cover a recently developed topic, exponential patterns in Ramsey theory. So this is broadly tagged under combinatorial number theory. So our goal of this presentation is to summarize some recent developments and some possible questions. So what is Ramsey's original theorem? So for any k belongs to k, let nk be the set of all subsets of n with cardinality k, but written in increasing order. Right? So if you have 1, 2, 3, then 1, 2, 3, 2, this means 1, 2, 1, 3, 2, 3, these types of element. Now Ramsey originally proved if k and r is given and nk is finitely colored, finitely coloring means finite disjoint partitions, then there exists an infinite set x and I belongs to 1 to r such that xk is in Ci. So Ramsey proved in 1927, and after Ramsey submitted his paper he died actually. Now Schur's theorem is one of the cornerstone theorem in this field. Schur's theorem says if n is finitely colored, then one of the color will contain a configuration of the form x, y and x plus y where x not equal to y. Now an immediate question appears, what is the infinitary extension of Schur's theorem? So for any infinite injective sequence xn, finite sum xn, this means a pattern of this form x1, x2, x1 plus x2, then x3, then take the summations and don't take summation, don't take repeated sum actually. So it was a conjecture of Sander which was later popularized by Erdos, Graham and Rothschild that such pattern is monochromatic. In 1974, Heinemann solved this conjecture using combinatorial methods, 10-page long proof actually. But soon after Heinemann proved this theorem, Baumgartner gave a very short combinatorial proof, and then Gelvin and Glaser found an ultrafilter proof, and then Furstenberg found a dynamical proof. All these three proofs influenced a new branch which is known as infinitary Ramsey theory. That means you are trying to find out an infinite structure in Ramsey theory. Now exponential Schur theorem, this branch was developed in 2012 when Alexander Sisto using ultrafilter methods proved that for every two coloring means A union A complement. So this is a two coloring. For every two coloring of n, there exists a monochromatic pattern of the form x, y, x to the power y, of course x not equal to y. Then in 2017, Julian Sahasrabudhe proved that this theorem holds for every finite coloring. So it was a conjecture of Sisto, and in 2017 Sahasrabudhe proved it, that for every finite coloring of n, there exists a monochromatic pattern of the form x, y, x to the power y. Now what he actually proved? He proved a monochromatic pattern of the form a, b, a into 2 to the power b. Now you can pass to the coloring, n goes to 2 to the power n, then you have x, y and x to the power y. Then in 2020, Dinoswa and Ragosta found a short ultrafilter proof of this theorem. Now exponential Heinemann theorem. So an immediate question is, what about the exponential version of Heinemann's theorem? So in 2021, Dinoswa and Ragosta proved this result using ultrafilter methods. Now a possible question. In 1974, Milligan and Taylor independently proved a joint extension of Heinemann's theorem and Ramsey's theorem, today known as Millikan-Taylor theorem. So it's quite complicated statement. See, nk, you are taking finite coloring of nk, then there exists an injective sequence, infinite injective sequence xn, such that this pattern is monochromatic, where h1, h2 is strictly bigger than h1. This means maximum h1 is less than minimum h2 in this way. So for k equal to 1, this is strictly Heinemann theorem. So this is known as Milligan-Taylor theorem. So what a possible question is, does there exist a Milligan-Taylor type extension of exponential Heinemann theorem? So for fix a sequence xn, then define xf is equal to xik to the power xik minus 1 to the power xi1, where f is equal to i1 bigger than in1 in this. Then this following question is still open, we don't know the solution. Another possible question is, I forgot to write in here. So actually in 17th decade, Erdos and Graham proved if you take an infinite coloring, then there exists x, y, x plus y such that either this entire pattern is monochromatic or all the colors of x, y and x plus y is different. So, either this is monochromatic or all colors are different. This is called rainbow. Now, the question is, what about the exponential version of this theorem? So, x, y, x to the power y, either that should be monochromatic or that should be rainbow. It is another question. The proof is short, I mean the talk is short because the topic is just developed. Injective sequence. All elements are different. Different. I mean x1 not equal, xi not equal to xj for all ij.
You mean x for h1 means multiply all the elements of h1?
No. So, oh, so x h1 means this type. Yes. So, if h1 is equal to suppose 1 2, then x1 x2. Okay. So, if h is equal to I1 I2 I3, then xi1 xi2 xi3.
Yeah, but the set is same as I2, I1, I3. So you're taking that's by order, is it? So inside that you reserve the order in there.
Yes.
So it's a tuple. H1 is a tuple.
Tuple. It's a tuple. Yes. So if h1 is equal to 1 2 and h2 is equal to 3 4, then xh1 xh2 means x1 x2 x3 x4. So this is exactly exponential version of Ramsey's original theorem, sorry, Millikan-Taylor theorem. But we don't know the solution. I think the solution, there should be a solution, I think. So this one.
Finally, injective sequence, you could have, instead of taking xn to be a sequence, you could have taken as a set. No?
Xn, it is a set. Yeah. Yes.
Can we
Yeah. Oh.
change the condition for plus like x, y, x plus y to make it like x, y, x into y?
Yes. So pass n goes to 2 to the power n, then this immediately gives you x, y, x to the power. Sorry, x dot y.
We can get any function to be there, like
Which?
x, y, f, x, y.
No.
Not like exponential, but like a polynomial.
I mean, for all functions that is not possible. So you have to classify. Classification of such functions is itself a